Uh, for those that I haven't had the pleasure of meeting yet, my name is Lee Byron. I work at Facebook on a team called Product Infrastructure. And Product Infrastructure at Facebook is responsible for researching kind of the large problems that we face as product developers and application developers, which the outcome of which is often libraries, tools, patterns that we end up using in production at Facebook, but we also ultimately open source. So a lot of the work that I've done over the last few years has either ultimately become open source or has been open source first. And that includes React, GraphQL, and Immutable.js, which I get to talk about today. How many of you have used React before? Awesome, that's like almost the whole room. If you haven't used React, don't worry. This talk actually doesn't have that much to do with React. If you have used React, then you'll just get a little bit more intuitive nature of some of the examples that I'm going to show you. How many people here have done something with functional programming that had immutable data? All right, like maybe half of you. How many of you know how that actually works under the hood? Good, then you're going to learn something today. So we're going to talk about immutable data and why you should use it in general, not just with React, but in a lot of different applications. Immutable data has been kind of locked in this realm of academia for a while, but it turns out that it has lots of really awesome properties for exactly the reasons why we should care about it as product developers and application developers. So Immutable.js is a project that I started about a year ago. It provides implementations for immutable collections built in JavaScript that are inspired by the same collections you would find in Clojure, Scala, Haskell, a lot of these functional programming environments. Despite being a year old, it's a pretty young project. There's still a lot to do. There are more data structures to build. There are performance improvements to be had. We are relatively bug-free now. There's a pretty good test suite, although every once in a while somebody reports a bug. But we're pretty thrilled with how people are using it, the response. We've got something like a little over 8,000 stars on GitHub, which I'm very happy with. And there's still more to do. So this has been a lot of fun. I'm going to go through the presentation today in a little bit of a weird order, but only because I want to show you some code. So first we're going to talk about how these things work. And then later we'll talk about why. So I'm going to explain what's so special about these things. And then later we'll talk about patterns for their use, problems that they solve. So kind of trust me for a minute. These are useful. OK, so what are these things exactly? The long term for these is persistent immutable data structures. And that's a lot of words. Immutable means that once you create one, you can't change it ever again. That should make sense. Persistence doesn't have anything to do with like writing to a disk or something like that. What we mean in this context is that we can present what appears to be a mutable API that looks like it should change things, but in fact what it does is it returns a new version of that thing with the mutation applied, and it does not change the original. It maintains its immutability, and we can continue to use the previous copy. And let's look at a simple example. This example comes from Immutable.js in JavaScript. So we're going to get a list collection. We're going to create a list with 1, 2, 3. And then we're going to push on 4. So push looks like it would be immutable behavior. But you notice that it actually returns a new list. And if we look at the original list, we see that, in fact, it did not change. And this is, in fact, a different object altogether. And the result of this, our list 2, is in fact the list 1, 2, 3, 4, which is what we want. And we can continue to use that. And these are not the same. And so that's what persistence means. So conceptually, you can think about how we would implement these methods as first making a copy, then applying the change we actually want to change, and then return that copy. And all persistent mutable methods work in this fashion. And so you might be thinking to yourself, as you're reading this code, that sounds pretty slow. My app has performance as a primary characteristic. That's too bad we can't use this. But if you've used React before, there's sort of a similar initial negative feeling of, wait, you're going to re-render my whole UI if anything ever changes? That must be slow. But of course we know that it is not slow, because while we can present a very simple interface, we can implement that interface using lots of really interesting techniques to do this in a very performant way. So I want to talk about the difference between interface and implementation with regards to these structures. And I want to point out a little bit about the end result of this first. So these are some performance numbers. On your left-hand side, you see JavaScript's native mutable array. And on the right-hand side, you see Mori, which is a library that exports the really awesome immutable data structures from Clojure. And we run the same code over this. So all we're doing here is we're making a list, and then we're building it up so it's a list from 0 to 1,000,000. And this turns out to take about 83 milliseconds in just plain old JavaScript, and it is somewhere around the ballpark of 4 to 5 times slower if you use immutable data. So is immutable data slower? Yes. You will never beat the performance of just munging on mutable memory. But tell me if the push operation is the bottleneck in your program. I guarantee you that the push operation is not your bottleneck. So it is okay to have a 3 to 5x penalty on some of these methods if it means that we can reap large performance improvements, often by changing not just a constant factor, but turning exponential things into linear or linear into constant. So let's talk about how that works. The implementation. How do these things work? So we use a technique called structural sharing. Structural sharing means that when we perform one of these mutative behaviors, what we want to do is recycle as much of the previous data structure as possible. So if you push onto a list, what we'd love to do is copy the memory, like literally just reference the exact same memory from all the parts of the list that you didn't change, and only replace the bit that you did. There's a certain kind of data structure that lends itself to this behavior, and it's called a directed acyclic graph, or a DAG for short. It'll look something like this when you can draw it down on paper. So anything that looks like a DAG can take advantage of the structural sharing technique. I'm going to illustrate a little bit of what I mean by this. We're going to edit this graph. We're going to change this node, okay? Since it's immutable, we can't just change that, right? Because that would change our tree. We don't want to do that. So we actually want to make a copy. And notice that it's pointing down to this other node, and we can just continue pointing to that same node. We don't need to copy that node, so that's shared. But of course, we now have to point to this new copy, and yet again, we can't mutate that, so we have to do the same kind of trick. We'll make a copy of that node as well with the new pointer to the other new node. And we repeat this process until we get to the root. Same idea, pointing to the previous node that didn't change on that side. And now that we've done that, we have a copy. We have the new tree with this mutation applied that we wanted. And we can see here all of the stuff that is actually shared between these. And notice that the original remains completely unchanged. So we can use both of these at the same time if we want, even though they overlap in memory. Or if we don't want the old one anymore, we can just not reference it anymore, let our garbage collector clean up after ourselves, and we're left with only the modified version. And if you have an environment with a good garbage collector, all modern JavaScript VMs have a good garbage collector, then this is a very performant process. Okay, so DAGs are pretty cool. That was a cool trick that I just did, but I don't know how much of your program looks like a DAG. Most of my program looks like arrays and objects. And unfortunately, arrays and objects are implemented, they look something like this. Arrays are usually vectors under the hood. Objects are usually hash tables under the hood. And neither of these things are DAGs. So we're in trouble. Luckily, again, for us, there's a pretty cool data structure called a tree. And it's short for taking the kind of middle bit of the word retrieve. And it makes building these kinds of things really efficient. And it is a DAG. So I'm going to illustrate a couple kinds of DAGs that let us build the structures that we want. The first is called an index tree. So an index tree holds not just values, but nodes of nodes of nodes, where each node is an array. And this is an array. It looks like a tree, but here in the leaves are our values. We don't care about anything up beyond that, but if I were to do a depth-first traversal and walk through this tree, I count from 0 all the way to the length of my array. So this, in fact, looks like an array. And in fact, depth-first traversals are pretty cheap, so iterating through my array is just about as cheap as it is to iterate through a regular array. And accessing an index is also pretty fast. Here's how that works. Say we wanted to get index 141. What we're going to do is we're going to turn that into a binary number. Once we have the binary number, we can shift through the bits. So we're going to look at just the first 2 bits here. Right? So this is going to be a number between 0 and 3, or indexed 1 through the 4th slot in here. So 1, 0 is the 3rd slot, 0, 0 is the 1st slot, 1, 1 is the last slot, and 0, 1 is the 2nd slot. And lo and behold, we have found index 141 in our tree. Similarly, if we want to set something into this, same process to find our index, same process to create a copy with structural sharing of this DAG with the mutated node there in the leaf. And we have a new version of our list with the mutation applied. And so now we have a list. And this is a way of creating the interface of an array, but using all the techniques of structural sharing and efficient immutable data structures under the hood. Similarly to that, we have a structure called a hash tree. And a hash tree gives us a map similar to how an index tree gives us a list. So hash tree, similar kind of structure. We have arrays of arrays of arrays down, although at any point we can have a value node. And a value node actually holds both a key and a value, since this is going to represent a map for us, like a dictionary. So in this example, I'm using some letters as keys, and I'm using some 3-letter strings here as my values. And once again, I can iterate through this. So if I want to iterate through all the key value pairs in my map, I can do that in a linear fashion by doing a depth-first traversal of this structure. But of course, note that there's no inherent ordering to this. So as I put stuff in there, the iteration doesn't have order in the same way that index tree had an explicit order. So we're going to need a new trick in order to find our way around this structure. We're going to need a function called hash. And this is fairly common in a lot of languages, although this is a fairly new thing for JavaScripters. Hash is a function that, given any value, returns us a number, expressly a 32-bit integer that we can then treat as binary number and do our same magic with. And we can hash all kinds of stuff. So we can hash strings, we can hash other numbers, we can even hash other data structures. So we can hash this list of 1, 2, 3, and that has a number as well. So let's get. We want to get whatever value is at key r. So first thing we want to do is we want to hash r and get our number. In this case, it turns out to be 82. So we're going to represent that as a binary number. We're going to do the same trick, although this time we're actually going to walk in a different byte order. So we're going to walk from the bottom of the number upwards, but otherwise same technique. So 1, 0 is the 3rd slot, 0, 0 is the 1st slot, 0, 1 is the 2nd slot, and hey, we found a value node. We didn't even have to finish iterating through that whole number. As soon as we find a value node, we're going to look at the key, make sure that it matches the key that we were after in the first place, and since it does, we know that in fact we have our value. Similarly for sets, we want to add something here. So we're going to look for key h. If key h doesn't exist, we're going to create the proper nodes to put it in there, and then we're going to set the value hat. So step 1, let's hash that. Here's our binary number. We're going to walk up, and very first step, at index 0, we have a collision. Something is already there. Here's how we're going to fix that. We're going to go to the next set of bits. We're going to push down. Notice that I did not edit the original. I just kind of visually made space here to draw this. but the structure of the original remains unchanged. I'm going to insert a new node, and what I'm going to do here is rehash the original conflict, make sure that there's a pointer to that in the right space, and then at my 0 or 1, 0, sorry, which is slot number 3, insert what I wanted to. If this also collided, I would just recurse and do this again until I got to a non-colliding spot. And now I have my value in the tree, and I have a map. So if I want to create associations between keys and values, or if I want to have lists of values, now I have 2 data structures that do that, that also have the characteristics of structural sharing to give us highly performant immutable data structures. So we have implementations as a tree, but if you use these things, you'd never know that because you only ever use the interface to use them as lists and maps. All right. Why is this important? Why do we care? Hopefully you guys found that interesting. I liked the visualizing what's going on under the hood. But we only care about this if it solves problems for us as real developers. At the end of the day, my job isn't just to come up with cool slides. My job is to empower developers, not just at Facebook, but worldwide, to build stuff in great ways. Well, immutable data structures are great. If you've done functional programming, you know that it solves all kinds of interesting problems for us for concurrency. And if you were at the Rust talk earlier today, you heard a lot about how using immutability is one way to solve this problem, shared mutable state being the root of all evil. And even this phrase came up, so something must be in the air. Multi-threading is just like this crazy space. It's full of pitfalls, full of foot guns. You're going to get yourself in trouble unless you have good tools for this. But kind of lucky for us JavaScripters, we don't have to deal with that yet. But also, unluckily for us, that creates a big problem for JavaScript. CPU speeds have increased for a long time, but we're starting to see the end of CPU speed increase and the beginning of CPU core increase. And that is especially made clear as our devices get smaller and we jump down the CPU speed timeline in order to preserve battery life, but we continue to add cores. So JavaScript's only capable of accessing 1 core at a time on your device, and this is a big deal. And a lot of the reason why as the JavaScript community hasn't taken advantage of multi-threading is the baked-in data structures that we have are mutable by default, and JavaScripters are just not well prepared to handle the multi-threading perils. So this is not a solution to this problem, obviously, because this is just a user library that I've made. What I want to do is start a cultural shift in the way that we build software so people understand why immutability is important and start to leverage these things, build applications in this way, so the powers that be that build our web browsers will start to give us first-class primitives that, in fact, embody the same techniques, and then build multi-threading principles on top of them so we can enable JavaScript's future. This would be great. But it still solves problems that we have today. Multi-threading is a big one, but there's another one that I really want to talk about that I think goes often unsaid underneath all the concurrency issues that it already solves. And that's tearing apart values from time. If you've ever watched any talks from Rich Hickey, you've heard him beat this over the head over and over and over. And I won't continue to do that more than I have to. But certainly if you have not watched talks from Rich Hickey, please go check them out. They are all amazing. This is a huge problem. The idea that a value can change over time just completely expands the amount of stuff we have to think about as developers. It means every little bit of your code can be a state machine. And state machines are hard. Rich has this concept that I really like of separating 3 concepts: identity, value, and time. Here we have a variable. The variable is called identity, which is convenient for me, and that's going to be the R identity. There are 3 values that identity can have over time: value, next value, and future value. Am I mutating any values here? No, I am not. Over the time of the progression of my program, this identity has become associated with different values, which is very different from, say, identity equals the string value, and then I munge in that data and actually edit these things. So JavaScript actually has immutable data structures, but we only use them for strings and numbers right now. It'd be great if we had more compositional data structures as well. Immutable data removes complexity. If you've worked with strings and numbers in JavaScript, then you're just like, no, they're easy. They're just strings and numbers. But if you've used strings and numbers in other environments where those things are actually immutable, then you understand the amount of pain that can come from not having immutable primitives. If we can take that a step further and have our data structures exhibit those properties as well, we can remove huge amounts of potential problems from our software as a whole. This is really great. There's this problem that I call the many mutators problem. Other people call it the shared mutable state. People say this is the root of all evil in software engineering. And it's probably true to some degree. But at the same time, it's easy for us to say that in an academic sense, and we know that this causes bugs for us, but at the same time we say, but having shared mutable state allows us to do a lot of things, and having shared mutable state allows us to build things in a very performant fashion, and you're griping about all this stuff, and you're making a big deal about it anyway. And to that I say, you all have Stockholm Syndrome. This is totally terrible, and as soon as you see the light and you stop using mutable data structures as the default and instead use immutable data structures as the default and only use mutability when you absolutely have to, you realize that these massive class of errors all go away, and you're going, oh my gosh, all that time I thought I was doing that because that's the only way to make fast software, and in fact that couldn't have been further from the truth. So I want you to look at this bit of software and tell me what will log to my console. Show of hands, how many people think the value, string value, will come out in my console? None? Okay. How about the string key? All right, good. Nobody said that was the trick answer. How about who the hell knows? That's the correct answer. Who the hell knows what comes out here? Of course, this is a problem, but this is a problem not just because this makes this hard to read for me as a programmer, but there's this problem that we deal with all the time as user interface engineers of dealing with what has changed. So some amount of arbitrary work has happened somewhere else. I'm responsible for rendering a UI, I get a new value, and now I'm responsible for updating my UI, except updating UIs is expensive. I gotta draw stuff to graphics, I gotta move stuff around. I really wanna do as little work as possible, and so what I'm gonna do is figure out only what changed and only update what parts of my application I have to. Every single UI framework deals with this problem. Okay, so this is the exact same piece of code I showed before, but I've reshaped it a little bit to deal with this problem of rendering in UI. So now I have the same kind of idea, but I've called it data store. And what I want to do is render something, and now I'm going to load some data into my data store by calling a URL, and then that's going to call me back when it's done, and then I'm going to render the UI for this data store. Render UI is going to have a really hard time figuring out what to do, right? Data store is a mutable JavaScript object. Load data into store could have done any number of things to that, including just setting it to be a null. And render UI is just going to have to make no assumptions at all. But we have solutions for this, right? You may have heard of this proposal called object.observe. It's a proposal for the next version of JavaScript, and it's actually been implemented in Chrome for a little over 2 years. So people have been able to play with this for a long time. And this is how we would solve this problem with object.observe. So we're going to render a UI. We're going to observe the data store. And when there are changes to the data store, then we're going to re-render the UI, and we have this handy extra bit of data that we can pass to that function. And now when we call load data into store, we don't even care about it coming back. All we care about is if load data into store actually edits the data store, then we'll figure that out because object.observe will fire. But this kind of bothers me because I'm not entirely sure what changes is going to hold. I'm not sure how it relates to data store as a bit of information, and it's not entirely clear what that's going to look like. And if you've used React before, you know that this is actually the opposite of what you want. Rather than given an explicit set of deltas that has occurred, what you really want is just the new value to rerun your render function. But there are some serious problems with this beyond just that. Here's some simplification of some code. I got some data. I'm going to observe it. And when there's a change, I'm going to do something expensive, for example, update a UI. And then I'm going to go do, set this field, set that field, set that field. What happens here? Does this call, the expensive call 3 times? Does it wait until the stack frame has ended and call this 1 time? The answer has changed over time as we figured out the proposal. There are trade-offs to both of these. And I would argue that this is a very confusing piece of code. We also can observe deeply. So if we have our data store here and we set deeply, data.foo.far.a equals something, object observe actually does not fire. So we would solve this intuitively by, let's not just observe, let's observe deeply. So I created this function that will call object observe, and then it will iterate over the keys, and if it finds another object, it will also observe that, and it will recurse. So we get really nice, totally deep object observe. But then we can do this. We can pull a previous value out. We can replace that with a new object. And now when we call data.foo.val and set something there, we're not going to hear anything about it. That should have like an equals something probably. And if we take our previous value and set something in, even though we've taken it out of our data store, our handler will still fire. Probably not what we expected to happen. So there's some pretty serious problems with object observe because of these. I just pointed out a few. And actually because of this, and for other reasons, it's no longer a proposal. As of Monday, actually. On Monday, the original author of Object Observe sent a message to the standards body for JavaScript saying that he was officially rescinding his proposal for Object Observe. He no longer thinks it's a good idea. It made me very happy. OK, there's a different way to solve this. Dirty bits. A lot of frameworks take advantage of this technique. So what they want to do is say, I have a model, and it has a flag called dirty, which is going to init to false. And I hold away my data somewhere that you can't get to, and instead you have to access it through getters. In JavaScript, you can just have a get function. In other languages, you might actually have like a getter property function. And what I'm going to do is I'm going to look up that key. But when I set, what I'm going to do is I'm going to flip the dirty flag. I'm going to say, since you last looked at this, this bit has been changed to true, and you need to assess to see if something has changed in here. And then this is going to coordinate with my rendering library such that I can check this dirty flag. And if it has not been set, then I know that nothing has happened, and I can just skip whatever I'm about to do. Otherwise, I'm going to make sure that I say, I've been here. I'm going to mark this as no longer dirty. Then I'm going to go render my UI. And this is pretty cool. I can update my UI. I can call it a bunch of times, and they all become no-ops. I can call set. I can render my UI, and I get my updated UI again. So problem solved, right? We can all go home. But if we try to render this data in two places, then we can pretty easily create a bug. And frameworks end up trying to handle this for you by putting a lot of code on top of you. And if you notice, this is a major reason why React is a lot smaller than a lot of the libraries that came before it and does not enforce any kind of model class on top of you, because this whole problem goes away. We don't want to couple model classes to view classes. I don't want to be forced to use a special kind of thing to represent my data, because we already have tools representing data. We already have objects and arrays. And then, of course, Immutable.js, I want to be able to take advantage of these things in my program. And it totally sucks if I really like my view library, but in order to use it, I can only use this one model structure. So I think immutable data, it gives us a much better way to solve this problem for UI programmers, change tracking. Check this out. We're going to get a map. Here's a new map with key to value. I'm going to create a second map, and I'm going to set key to foo. So the first one has remained unchanged, and I get the second one. And I can just compare them, just like equality check. And it turns out these are, in fact, different values. And then if I take that and I set key to value, it'll say Immutable.js is clever, and it says that's already the case. So rather than create a new structure for you, I'm just going to return exactly the same thing. And then you can compare them, and it turns out, in fact, that they are equal. This check is very, very cheap, bordering free. And we can do even more complicated stuff. So if I have deeply nested maps, so here's maps of maps. And we have this method called setIn. So I can say I want to set the value within foo to 500. So this is going to return me a new deeply nested data structure. And that, of course, means that this second data structure is not the same as the first one. And if I look at the foo property of the second one and the foo property of the original, of course, they are not the same because I changed that value. But if I go check this unrelated bit of data, right? I didn't edit bar at all. And I can go look and see, in fact, that that is exactly the same bit of information. This solves change checking for us. And this is important because now we can take advantage of this technique called memoization. And I'm sure you guys have heard about this before, but have you ever actually had to implement it in JavaScript? How many? Only a couple hands. It's because it's really hard. This is just going to be an example. We're going to take a list, and we're going to sum all the numbers up. So reduce, and then add all the numbers in the list. And I know that if I have a really long list, this might be slow, so I'd really like to memoize this, please. So I'm going to call a function called memoize. I'm going to pass in, oops, that should say sum, not raw sum, and get back memo sum. And then I'm going to call this a bunch of times, and I would like to give it this array from 1 to 1,000,000, add it all up, push a value in, call it again, and get the right answer. And so I went looking for this function, memoize. You know, this is a common thing. Someone must have implemented this before, and I went Googling for it. And the first response was from Stack Overflow, and it had like 180 upvotes. And this is a relatively simplified version of the code because they allowed multiple arguments, and I'm only allowing one, so it fits on the screen. But this is more or less exactly what they gave us. Can anybody see why I thought this was awful? Anyone? Just shout it out. No? Stares me in the face. What? JSON stringify? That's an order n operation. On the input to the function that we're trying to memoize over, which means we think this is going to be slow because the inputs are large. And so we're avoiding potential order n operations to memoize by doing an order n operation on every call. This completely defeats the purpose of memoization. This piece of code is trash. So I went to go re-implement this myself, and I came up with this implementation here. I'm going to take the argument. I'm going to check it against the last time I called with just regular equality here. And if they're the same, then I'm going to return the previous result. Otherwise, I'm going to set the arg to the previous arg, and I'm going to call the original function, set that to my previous result, and return that. And this means that if I call it multiple times with the same value, I will get back the previous result. So this is a fairly simple version of memoize. There are a lot of different shapes memoization can take, and this is a simple one, mostly just so it fits on the screen. And now I can do what I want to do. So I have an array of 1 to 1,000,000. I'm going to time this, so I'm going to sum it up. And sure enough, the second one I call sum, and while the first one took 60 milliseconds, the second one was some number of nanoseconds, so it's basically free. And then I'm going to push into my array, and I probably didn't expect it to be free. I thought it would recompute, and in fact, it gave me the wrong answer. So my implementation is fast, but it doesn't work. Can anyone tell me why it doesn't work? That's exactly right. This does not work if you pass the same array in twice, because of course the same array is equal to itself, and I mutated the array when I called .push on it. So the array is the same as itself, and it says, okay, that's the same arg you gave me last time. I'm going to use my cached value and send it back. And it didn't know how to detect that a change had been made to that array. Let's try this again, but use immutable list. So we're going to create a list. We're going to do the same thing, exact same implementation of memoize, exact same implementation of sum. But this time, instead of an array, we're going to create a list from 1 to 1,000,000 that is immutable. Same operation here. I'm going to sum that list. Here you see the performance penalty of using immutable data structures. As it turns out, depth first traversing a tree is, in fact, slightly slower than iterating through a block of memory. So we get 75 milliseconds instead of 60. But we get a right answer, and we call it the second time, and sure enough, a couple nanoseconds, it is free. And then we push in and make sure that we take the return of that and set it. So list is our identity, and we get a new value, and we assign that to the list identity. And we call memo sum again. And as we expect, it takes some time to process, and we get a new answer. Yay, this is what we want. All right. This is cool because if you've used React before, you may have heard of this thing called should component update. Should component update is called every time your application is going to re-render. Not render for the first time, but re-render. And what it's going to give you is the state of your application from the last time we rendered, and the new state of the application we think it's going to be later. And all we want you to give us is a yes or no answer. Should we re-render this piece of the application or not? The default implementation for this is true. Always re-render. Why? Because if we got this wrong, we would just get a zillion bug reports that, I don't understand why my thing isn't updating. And of course, JavaScript is full of mutability, so there's no assumptions that we can make here. We just always have to return true. But you can override this function if you want, and you can provide an implementation. And so I wrote one that uses this thing called shallow equal. Props and state are both going to be plain JavaScript objects. What I want to do is actually walk through each of those, look at the keys, look at the same key in the next structure, and compare those values. And if each of those values is just using triple equals equal, then I'm going to call that shallow equal. So what this says is if either props or state is not shallow equal, then I definitely want to re-render. Otherwise, I can skip re-rendering. And here's a slightly shortened to fit on the slide, but almost exactly full implementation. We're going to look through all of the A's keys and check them against B's keys, and then we're going to look through B's keys to see if any were actually missing from A, that we added any of them. And otherwise, we're going to say that they're equal. But note, same problem, right? Just raw equality check. So we can't use this with any kind of mutable objects. And by the way, I took my implementation of this and I wrapped it up and I put it in React add-ons, and so you can use this thing. It's called pure render mixin, and it will give you exactly the implementation that I just did if you'd like to use this. Have any of you heard of Ohm? A couple hands? Okay. Ohm is a wrapper around React for the Clojure environment. So if you like writing Clojure and you use Clojure script and you would like to build a UI using React, definitely check out Ohm. It is super cool. But really, it's just a very thin wrapper. It's just about getting the API of React exposed into the Clojure environment. And Ohm is actually faster than React. Despite being a thin wrapper, Ohm is way faster than React. How does it do this? It is faster because of immutable data. Because Clojure environments, a functional programming language, their data structures are persistent immutable data structures, actually with very similar implementations to the ones in Immutable.js. They do not have to return true by default for should component update. They have pure render mixin turned on by default. And so reconciliation, the process by which we take two versions of React View, combine them together to figure out what we actually need to do to the DOM or to the underlying UI infrastructure. Reconciliation is really fast. This is why React is used, and people say, the best feature is performance. I think the best feature is simplicity and composability. It helps that it is also fast. But reconciliation is slower than memoization. Memoization is almost free. Reconciliation is good, but memoization is better. So Flux is a name of this pattern for having data moving only in a single direction. It's not really a new idea, and it's a pattern kind of in the same way that MVC is a pattern. So there's many, many implementations of this idea, and we've been looking at a bunch of them, and Flux was an idea that came out of Facebook with our use of React. And in my opinion, a lot of implementation of Flux have a really serious flaw. It's that they contain mutable data under the hood. So even though data is moving around in a single direction, we're very careful not to do these mutative calls within our APIs. Under the hood, they're still mutable, which means that it's really hard to answer the question of what changed. So what most Flux implementations will do is they'll fire some event at you. They say, data that I know about has changed. Here's the new data. Do what you will. And if you're a React component, you'll say, like, all right, I'm going to re-render. What you'd really like to do is say, you told me that it changed, but did it really? Or if it did, what little bits of it changed? So again, reconciliation is fast, but let me illustrate this. I'm going to illustrate it with our favorite example. This is the hello world of UI frameworks. This is the to-do app. In this to-do app, this is like the most basic implementation of Flux. And actually, I stole this from, there's like the to-do MVC project, and somebody has implemented, actually I think Pete Hunt implemented this version that is a simple implementation of Flux and React. So basically what's going on here is we have a store of data, and that's just represented actually by this little variable to-dos, which is a plain JavaScript object. And then what we do is we listen to incoming events, we do behaviors, and then we send outgoing events. So the dispatcher takes our incoming event, we check to see if it's a create action that's going to create a new to-do. Then we're going to create a new to-do item. We're going to stick it in the to-dos ID. So it's going to become a addition to that map there. And then we're going to emit change, and then we're going to go do some stuff with our app. Yeah, that is what I said. OK. So this is what that looks like. Let's send a create action. All right, so we're going to add a to-do. This is what I want to do later today. And React is going to go reconcile. It's going to look at all this stuff, reconciling through. And there we go. We got to add that. And it's going to create a change action, apply that to the DOM, and then you'll have the updated UI. Cool. Let's add pure render mixin. In order to add pure render mixin, we're going to need immutable data. So let's change Pete Hunt's implementation of Flux to use Immutable.js. So here's where we started. Nothing changed yet. What I'm going to do first is replace to-dos from a plain JavaScript object with something called an ordered map. So whereas before I was saying you iterate through a map, and it's not necessarily going to be in any guaranteed order, ordered map, you'll iterate through the keys exactly in the order that you added the keys into the object, which is the same behavior as JavaScript objects, for better or for worse. So this is going to give us exactly the same behavior. Step 2, rather than doing to-dos at ID equals, we're going to call a set action and then take the result of that and overwrite our to-dos object. And then we're going to add pure render mixin. We're done. That's it. OK, now when we do this, same thing. React's going to go reconcile, realize that none of that stuff changed. The only thing it changed at the end, it gets to skip very high, and it's a very, very cheap skip, because memoization is just a single pointer comparison. It's going to skip all that stuff and get here much, much faster. So in terms of Flux, applying the same idea, a Flux store is an identity. So the Flux store that holds all of the information in your application, that's the end identity, the data for my app. It's going to have new values over time, which means the previous values haven't changed. And that's going to be how your app works. And if this is at all interesting to you, you should check out Redux. Here's where you can go get this. It's built by this guy, Dan Abramov, who's super smart. And this is a very, very tiny library. And it implements a lot of these ideas. And it makes it really nice to use. And I have like 1 minute over time. But I want to show you this last thing, because it's super cool. Undo. If you've ever tried to implement undo in your application, it can be really hard. And the only reason that it's hard is because mutability. If you have persistent immutability, it's really, really easy. So here's where we left off. We're going to add undo. First, we're going to create history. I'm just using immutable array. That's fine. I could have used an immutable list, but in our case, it doesn't even matter. We just need somewhere to stash old values. Now, when I call create action, what I want to do is I want to take my previous values of to-do, I want to stick it in history. So this is going to be kind of my stack. And I'm going to add a new kind of action called undo that I'm going to call somewhere from my program. And when that happens, all I'm going to do is pop from my stack of to-dos, set to-dos to the thing that came out of pop, and emit my change. That's it. Now I have undo working across my entire application. All I got to do is send an undo event to my dispatcher. If you ever tried to do undo and it took you more than 45 seconds, I'm sorry. Now you can do it this way. All right, so to overview, this is persistent immutable data structures. While they may appear slow from the get-go, under the hood they can be made very, very fast because of this technique called structural sharing. This allows us to get rid of our mutable state Stockholm syndrome without giving up performance. We can solve problems by removing complexity rather than by adding it. And I think that is something that is very exciting. Thank you very much. Again, I am Lee. Thanks so much for coming.